Now let's discuss more about implicit functions. As you recall, we can have an expression or an equation that involves, for example, variables y and x. And it can be of this form, f of xy equals to 0. You can express an equation or expression in this manner. And sometimes it is easy to define y explicitly as a function of x, okay, given this implicit function. But there are cases when it's hard to do so. So it's hard to express y as a function of x explicitly. So in this part of the lecture, we'll deal with the conditions where you can express an implicit function explicitly, okay, at least in a restricted part of the domain. So for instance, we have this expression or this equation over here, f of xy is equal to y squared plus x minus 4 equals to 0. So this is uh, an implicit function of this form. Okay, so if we move things around, we put 4 and x to the right hand side, we have y squared equals to 4 minus x. Now notice that if x is greater than 4, then this whole right hand side of this equation is a negative, and therefore if you took the square root of a negative number, it's not a real number, okay, it's an imaginary number. So for values bigger than 4, this expression over here or this equation over here is undefined. However, for values less than 4, we can take the square root of y squared, and therefore y is equal to plus or minus square root of 4 minus x. Okay. Now notice that for each of x in this domain, for x less than 4, okay, you have two values of y as seen in this graph on the right. Okay, so for example, you have x1 over here. There's an associated y over here, call it y1, and there's an associated y over here, y2. Okay, so this equation doesn't represent a function. Now consider this neighborhood over here. If we can draw a disk or an open ball, u here, this is this broken circle over here, u. Now notice that when you have x0 within this interval of the open ball, you can express y as a function of x. So in this, at least in this area over here, in this restriction over here, in this ball, if you have one x, call it x naught, there's only one associated y over here, y naught. Okay? So in this neighborhood, v, defined by this small slice over here of x, okay, this is v. In this neighborhood, we can define y as a function of x. Okay, so at least in this neighborhood over here. Now, notice that for this neighborhood, uh, you can express all of the x's in this neighborhood has only one corresponding value of y, right? So in this neighborhood, you have different x's over here, which will only contain one value of y. So therefore, we can express y as a function of x for each of the x in this neighborhood u. Okay? But notice that if we draw a neighborhood around 4, 0, something happens. Okay? Now we cannot do we cannot replicate such exercise from this neighborhood u to this neighborhood around the point 4, 0, or x equals to 4, y equals to 0. So the question is, what's special about this point 4, 0, okay? Such that uh, you can express y as a function of x in this neighborhood over here. So at point 40, at this point over here, notice what happens, okay? So at this point, the curve sort of turns back. So if we have an upward rising portion here, then it turns back over here. Okay? So in this neighborhood, if we define a neighborhood U, okay, around the point 40, so there are some values of x, for example here, call it x1, okay? At x1, you don't have a corresponding value for y, okay? So meaning that it doesn't hit the curve when you're at x1. Okay, so this is what we had said a while ago. For values greater than 4, this function is undefined. Okay, notice there, notice then that if we have another x inside this neighborhood, okay, inside this neighborhood, for example, this one, call it x2. In this value of x, notice that you will have two values of y. So you have a y here, and then you have a y over here. Okay, so in this case, you cannot explicitly um, express y as a function of x, because for each x in this to the left of 4 in this neighborhood, okay, there are two values for y. So it's either when you're right to the right of 4, when x is to the right of 4, it's undefined. To the left of 4, around this neighborhood u, there are two values of x. So in this case, there is no way you can express y as a function of x in this neighborhood u. So moreover, notice here that if we were to draw a tangent line at the point 40 of this curve, you notice that that tangent line that just touches the curve at point 40 is vertical. Okay, so it's this vertical line. This tangent line is vertical. So therefore, the slope is infinite. Okay, so the rise is infinite. Okay, now we can see that when we look at the differentials for this implicit function over here. So if we take the differential, so we have f of x, which is partial f over partial x, okay, dx plus fy dy equals to 0. Okay, so this is just a differential of this implicit function. Now, if you move things around, we have um, fy dy equals to negative of fx dx. Okay, so if you uh, move dx over here, over to this side, and fy to this side, you will end up with this equation. Okay, so at x equals to 4, you know that the slope of the tangent line, by the way, this is just the derivative. So this is just the slope of the tangent line. You know that's vertical or infinite. Okay, so when will this happen? This happens whenever fy over here is equal to 0. Okay, so if we uh, uh, if we have our function a while ago, or our implicit function fxy is equal to y squared plus x minus 4 equals to 0. Okay, so what's fy here? Fy is just equal to, just take the derivative of this one with respect to y. This is just 2y. Okay, and y doesn't appear anywhere else. Okay, so you know that fy is equal to 2y. So once you evaluate it at the point 40, okay, so you evaluate it at the point where x equals to 4 and y equals to 0. So you substitute y equals to 0 here, then it's equal to 0. So therefore, at this point, the slope of the tangent line is infinite. So the bottom line is, at least for some restricted parts, okay, in some neighborhoods, it is possible to express y as an explicit function of x, okay, within a neighborhood. Okay. In this case, in our example a while ago, we had the neighborhood x naught 0 naught as 4 0. Okay, that was in the previous example. Okay. So the bottom line is that it's possible to express y as an explicit function of x within such a neighborhood if, okay, if we have that fy evaluated at that point, okay, at that point is not equal to 0. Okay, so in the example a while ago, we did a neighborhood of 4 0. Okay, fy at 4 0 was equal to 0. So therefore, at that point, 4 0, you couldn't express y as an explicit function of x. So this is the bottom line of the exercise we just did, but we'll go through a general expression of the idea. So what are the conditions to which you can express y as an explicit function of x? This is due to the implicit function theorem. Okay, so what does the theorem say? So suppose you have an explicit function fxy defined on an open disk D containing a point x naught y naught. Okay, so that open disk D is that broken circle U that we had in the previous slides. Okay, so if the implicit function is defined on that, on an open neighborhood, okay, containing the point x naught y naught, and these three conditions are satisfied, f at x naught y naught is equal to 0. Okay, so when you plug in x naught y naught, the implicit function is equal to 0. Okay, the derivatives fy and fx are continuous on that neighborhood D. Okay, and more importantly, fy, the derivative of the implicit function with respect to y, is not equal to 0 evaluated at the point x naught y naught. Okay, then what happens if these three conditions are satisfied? Then you can find, okay, so there exists a function f. You can find a function f defined on an open interval AB that contains x naught, okay, such that you can explicitly define y as a function of x on that interval AB. Okay, so if you put in f of x here to the implicit function, it will be equal to 0. Okay, and moreover, f, that function, has a continuous derivative on that open interval AB. Okay, so these three are the conditions that need to be satisfied, at least in some neighborhood containing a point, um, where you can find a function f that explicitly characterizes y as a function of x. So in this case, in our example earlier, we knew that at the point 4 0, okay, at the point x naught y naught equals to 4 0, this wasn't satisfied. So therefore, at that point, you can't define function y as an explicit function of x. Okay, so here are the three conditions given by the implicit function theorem. Now, uh, the implicit function theorem is silent on the functional form of f. Okay, it just says that there is an f. Okay, but what it does is to justify the use of implicit differentiation, which will be the subject of the theorem in the next slide. So here's a theorem. So when we have a function f that is differentiable, okay, such that y is explicitly expressed as a function of x, and f is defined implicitly by some equation, okay, f of xy equals to 0. That's your implicit equation, okay, And Fy and Fx are continuous, so they exist and they are continuous. Moreover, Fy should not be equal to 0. Then we can find the slope of the tangent line of f, okay, which is dy dx, simply by getting the derivative of the implicit function f with respect to x, divided by the derivative of the implicit function f, big F, with respect to y, that's f of y, and it's just a negative of that. So the slope of the tangent line of this function y equals to fx, where f is defined implicitly by f, is found this way. Okay, so you just get the derivative with respect to x of the implicit function, divided by the derivative of the implicit function f with respect to y, and take the negative of it. Okay, so we'll learn an application of this theorem. So let's discuss an application of the theorem that we had earlier. Now this is helpful when we talk about level curves. Okay, so suppose you have a function z is equal to a function, you have a equation z is equal to a function of variables x and y. Okay, so a level curve is the curve defined by fxy is equal to c. Okay, so the function is equal to a certain constant, a number. Okay, so for example, if you have a production function, okay, q of fkl, okay, so output is a function of inputs k and l, capital and labor. When we set a particular amount of output, say fk L equals to 10, okay? So that's a level curve, okay? Notice that you can define this implicitly by this equation, okay? So you have an implicit function over here where you have your function small f of xy minus c equals to 0. So that's of the form fxy is equal to 0, okay? So in this example over here, you can define, well, unfortunately, I have big F over here, but we can say F tilde xy. This is the implicit function as FKL, or FKL, okay? FKL minus 10 equals to 0, okay? Sorry about that. I had a capital F here, so there's a capital F here that may be a source of confusion. But the bottom line is you can define this as an implicit function this way. Okay, just move negative 10 to the left hand side. Now you have a function that's equal to 0, an implicit function that's equal to 0. Okay, so that's an example. So if the three conditions in the implicit function theorem holds, you can get the slope of this level curve. Okay, the slope of the level curve f as negative of the derivative of the implicit function with respect to x divided by the derivative of the implicit function with respect to y. So what's this one? From here, so fx is just uh, the derivative of this one with respect to x. So x only comes here, so it's f prime x. Okay. Fy, on the other hand, because y enters this implicit equation through the function small f, you have f prime, uh, I mean f prime x over here, f prime y over here. So it's the derivative of this function with respect to y, xy. Okay, sorry about that. But yeah, so this derivative is just equal to f of x. Okay, so get the derivative of f, big F. This is simply just a derivative of f with respect to x. And the derivative of this implicit function with respect to y is just the derivative of this function with respect to y. Okay, and then there's a negative here. So this is how you get the slope of the level curve. Um, we'll go to an example in the following slides using the production function that we had, production function example that we had. So like I said earlier, we will use this production function example. So we have output Q as a function of two inputs, capital and labor. Okay, so if we set a particular amount of Q, for example, FKL is equal to 100, okay, this defines a level curve which is called an isoquant. Okay, so the isoquant, by its name, iso is equal, so isosceles triangle. Okay, so iso means equal, quant is quantity. So each of the points in this isoquant, for example, this is the capital labor space. So we have L, we have K over here. This is a particular isoquant, IQ1. Okay, so what does this mean? Here we have, what does it say here? Here we have 100 units. Okay, so this is the isoquant associated with this one. So what does it mean? It means that the isoquants are combinations of K and L that would produce 100 units of output. Okay, so for instance, we have this amount of L, call it L1, and this amount of K, K1. Okay, so if we put in F, K1, L1, K1, L1, you put in this amount of L and this amount of K, it will produce 100 units. Okay, so for example, we have another combination called this L2 and this K2. Okay, so if you put in K2 and L2, it will still produce 100 units. So the isoquants are combinations of K and L that will produce a particular number of output, okay, or a particular level of output, in this case 100 units. So the higher the isoquant is, the higher the level of output. So for example, we have over here, call it L3, and this one, this amount is K3. Okay, now here FK3L3 will produce how much? Well, it will produce 400 units. Okay, so each point in this isoquant IQ4 will produce 400 units. Great. So that's what an isoquant is. Now, the question is, what is the slope of these isoquants? Okay, so what is the slope of this isoquants at some point? So at this point, okay, K0, L0, K0, what is the slope of the isoquant at this point? Okay, what is the slope of the tangent line? So by using the implicit function theorem and the theorem that we had earlier, that slope, okay, this is the slope of the isoquant dkdl. So it's how much k will change when l changes. Okay, so it's a slope. So the slope of the isoquant is just simply, again, you have this implicit function f k l minus c equals to 0. So this is your big FKL. Okay, so the slope dk dl is just simply, according to the function a while ago, negative of f uh, negative of f um, l over fk. Okay, so what is this? So remember, k is your y, l is your x. So this is equal to fy over fx over fy negative. Okay, so this is from the theorem earlier. So this is, according to the theorem, this is the slope is equal to negative of f of l, which is slope of which is the derivative of your function, implicit function f with respect to L, divided by your um, derivative of the function big F with respect to K. Okay, so in this case, f of L is found by getting this derivative of this function with respect to L, so it's just f of L. Okay, of course it's at a particular point KL, and f of k over here is just the derivative of this small function with respect to k, so it's f of k KL. Okay, because this is c, this is a constant, the derivatives of this implicit function would only operate through this function over here. Great. So this is how you get the slope of the isoquants. Okay. So if you plug in L0, K0, it will give you a number. That's the slope. So if we have a particular functional form for the production function, for instance, if we have a Cobb-Douglas production function, then the production function will be of this form. So you've encountered this before. Uh, Production Q is just a function of K and L, which is of this form. Okay. So once you put in K, you raise it to alpha, a number, you multiply it by L, raise it to 1 minus alpha. That's also a number, and multiply it by a positive amount A. So that's how you translate inputs K and L to outputs. Okay, so that's the rule, that's the formula, that's a function. Okay, so again, if you were to have a level curve, okay, which is the isoquant, so this is just the isoquant. The isoquant is defined by a particular output level. Okay, let's call that output level C. Okay, okay. So we can transform it into an implicit function, big FKL minus C equals to equals to FKL minus C equals to 0. Okay, so in this case, with the Cobb-Douglas production function, FKL is just alpha k a raised to the k alpha L raised to the 1 minus alpha minus a particular uh, output level C is equal to 0. Okay, so you can transform this in an implicit to an implicit function. Okay, now what is the slope of this isoquant? This is from earlier, from the last result that we had. So it's just, in this case, it's just um, the slope of, I mean, the derivative of the production function with respect to L divided by the derivative of the production function with respect to K and getting the negative of that. By the way, this is equal to Fk, getting the derivative of this with respect to K divided by uh, uh, Fl divided by Fk and getting the negative. Okay, so since it operates, the derivative of this implicit function operates to the function f, you have this result over here. Okay, so we have that. So it's just straightforward getting the derivatives, the partial derivatives to be exact. So dk over dl is equal to this one. Now what is the function, what is the derivative of f with respect to L? Okay, so this Cobb-Douglas function, f uh, KL is equal to alpha K alpha L1 minus alpha. Okay, so partial F over partial L, or F of L, is just simply you treat K constant, so A K alpha, and then bring down 1 minus alpha here, 1 minus alpha, and then we have L 1 minus alpha minus 1. Okay, so 1 uh, 1 minus 1 is equal to 0, so you only have a negative alpha here. This is the same expression as this numerator over here. Okay, that's f of L. Again, f of k, we derive it similarly. So f of k is just the partial derivative of the production function with respect to k. So we'll treat L as constant. So we have a, and then the derivative of k alpha with respect to k, it's putting down the exponent alpha, then k alpha minus 1, and then you treat L as a constant, L1 minus alpha. Okay, so this one is the same as the expression in the denominator. Okay? So you take the negative of that, okay, and then we can cancel some terms. So alpha, the letter a parameter a cancels out. Okay, so here we have an expression for k. So k alpha divided by k alpha minus 1. So k alpha times k alpha minus 1 is just the same as k alpha divided by k. Okay, so this is k alpha minus 1. So this k alpha cancels. You can put k in the numerator. So that's why there's k in the numerator here. Great. In the same manner, L negative alpha over L1 minus alpha is just L divided by um, L alpha. Okay. Now this one is can cancel out. So if you put, this is equal to the expression. If you put L alpha here in the numerator, you have L alpha, and then L negative alpha raised to the negative alpha is just the same as 1 over L alpha. Okay, and then you have a 1 over L here, so you have an extra L here. So L alpha cancels. That's why you have a 1 over L, which is this L over here. Then you have 1 minus alpha here and alpha here. So this is the 1 minus alpha and this is the alpha. Okay. So just by simplifying things, you arrive at this expression. 1 minus alpha, negative 1 minus alpha times k divided by alpha times L. Okay. So that's the slope of the isoquant. Now notice that the slope of the isoquant also depends on the k and L, on variables k and L. So if you have, for example, an isoquant like this, so this is k, this is L, the slope of this isoquant depends on the values L of L and K. So the slope here at L naught K naught is this one, okay? While the slope at L1 K1 is different. It's this one. It's a little bit steeper than at this level, okay? So the slope of the isoquant also depends on K and L. But that's how you find the slope of the isoquant when you start with a production function. In this case, a Cobb-Douglas production function.